Welcome back to School of Physics. Today, in this lecture, I'm going to discuss a few things like velocity and acceleration, as you can see in the polar coordinates. Okay, so earlier we were discussing the velocity and acceleration in Cartesian coordinates only, but we know in physics it is very much essential to know about the polar coordinate systems also. So for that we will be dealing with the velocity and acceleration in polar coordinates also. So for that, furthermore, we can discuss about force and its components in these coordinate systems as well. So to understand force and other kind of forces which are occurring in the nature, to understand them better, for that first and foremost we have to discuss and understand this very concept about velocity and acceleration also. So further, as the time proceeds, we will get an adequate knowledge about the concepts further. So first and foremost, starting with, we will be dealing first, I will be discussing the orthogonal Cartesian coordinate system. Cartesian coordinate system. Okay, so if we'll discuss this, we have to consider, for example, I am giving you a simple example. I will consider a particle along a circular path, along a circular path. For example, what I'm saying is that, say, this is the circular path which is along which the particle is moving. Say for example, this is the particle, and suppose that we at the center we are the Cartesian coordinate system is drawn like this, with its origin at the center of the circular path. Okay, so this is the Cartesian coordinate system and this is the origin of it. Fine. So this very particle, this is x-axis and this is y-axis. This is a plane coordinate system. Okay, so this very particle is moving along the circular path, making some angle from the initial stage. For example, it starts from this very point, and after some time it will cover a distance which is here. It will be calculated in terms of theta. Okay, so this will be the theta which it traverses along the time as the time passes. And furthermore, you have to keep it in mind that along this very axis you are taking the position vector r. Okay, this is the position vector, this along the particle from the center toward the particle, it gives the position vector. And along this very axis, this will give the change in this theta. Fine, change in the angle traversed by the particle with respect to time, within the time. Okay, this is the position unit vector and this is the angular unit vector, that is theta hat. Fine, so this is the xy axis, this is the orthogonal coordinate system. So we know, it is the basics actually, the position vector r for this point, for this particle which is moving along this circular path. Position vector r will be given as, say for example, from the center up to this circle, that is the radius of the circular path, or simply the circle, say it is a. Fine, so we have r will be equal to, r is the position vector, keep that in mind, r is the position vector, position vector, that is, it gives the position of the particle at any instant of time. Fine. So our vector is equal to a, this is the magnitude of the vector a multiplied by cosine of theta I is the vector, unit vector along the x-axis, plus sine of theta along the y-axis, unit vector along the y-axis. Okay, so from where it is got, it is very much simple. You can check it out here. For example, for any position vector, for any vector in the Cartesian coordinate system, how do we write it? Say we are writing r, it's a position vector here. So for example, it's any vector in the Cartesian coordinate system. It is represented by x component along, this is the x magnitude of the vector along x-axis plus along the y-axis. Say y magnitude along the y-axis is represented. This is the general representation of any vector in the Cartesian coordinate system. However, we can write it in the, since here it is moving along the circular path, it's moving along the circular path, so we can write it down as r is equal to a times x divided by a. I'm dividing throughout by a, okay, I plus y by a j hat. Fine. So x by a is here, this is the position vector, it is here a, here the particle is here, this is the origin O, and this is the along the x-axis, this is the x-axis here. So draw a perpendicular on the x-axis. Fine. From the Pythagorean theorem, what we can deduce, this is the theta. Fine. So cosine of theta will be equal to, this is the x and this is the y, for example, say. So cosine of theta will be equal to base by hypotenuse, that is x by a. Fine. And sine of theta will be equals perpendicular, that is y here, divided by hypotenuse, that's y by a. So y by a is sine and x by a is cosine. So r will be equal to a times cosine of I theta, cosine of theta I plus sine of theta along y-axis. That is what I have wrote here. Okay, this is simple, so understand to get this very thing. So here is the position vector in the Cartesian coordinate system. So r is equal to a times cosine of this and sine of this. Fine. Now we have to get the, I told you we have to calculate the acceleration and velocity. So to calculate acceleration, we have to know what its velocity is. And the velocity, what does velocity mean? Velocity means we write velocity as dx simple in the, if it's moving along the x-axis only, dx by dt. That is the differentiation of position vector with respect to time. Okay, so we have to differentiate the position vector with respect to time to get the what? Velocity. So differentiating with respect to time, that means dr by dt. That's also represented as, it's written down as r dot. Okay, this is the Newtonian representation. Keep it in mind. R dot means dr by dt. So dot means differentiation with respect to time. So differentiating this with respect to time, since a is the constant here, a is this, the vector, this radius of the circle path. Okay, so r dot will be equal to, this will be written as it is. Differentiation will be done on cosine of theta and sine of theta. Keep this in mind that theta is varying with respect to time. Okay, we are changing the theta. Fine. So we have to differentiate cos then theta also from the chain rule of differentiation. So you might have already done that. So cosine of theta differentiation is minus sine of theta into multiplied by differentiation of theta, that is with respect to time, that will be theta dot, okay, plus differentiation of sine, it is cosine of theta, and the differentiation of theta itself, what will be that? D by dt of theta, that is written as theta dot, along, this is along x-axis, that's I, this along j-axis, that is j. Fine, keep this out. A times sine of theta along I plus cosine of theta along j, theta dot, keep this at outside, so we will get theta dot here. Fine. So this will give the velocity of this very particle along the circular path, and this here we can, you have to remember this very thing, this gives the direction here, this gives the direction of increase or decrease, whatever the case may be, increase in theta, that's the angle. Okay, fine, this gives the direction of the change in the theta. So it may be represented, we can surely represent this very thing, it is denoted or represented as the unit vector like theta dot, theta hat. Fine, so this gives the change in the angle theta, this very component, sorry, it's minus times sine of this and plus times cosine of this. This gives the change in the angle theta. Fine, this is represented by theta hat. So we can represent this very thing as R dot will be equal to A times theta dot, and this is theta hat. This will give the velocity in Cartesian coordinate system orthogonal. This is an orthogonal coordinate system, keep it in mind. Fine, so we will get the velocity equal to this. Now we have to calculate the acceleration, and acceleration means the double differentiation of position vector. So first differentiation we got this, now we have to differentiation it again. We will differentiation this very equation again with respect to time. Say this is equation A, differentiating equation A with respect to time again, okay. So what will we get? We'll get differentiation, first differentiation we got this, then the double differentiation with respect to time, that we get double dot. So R double dot will be equal to what? A is still constant times, now again differentiation of sine, cosine, and theta, it's theta dot, we'll get cosine theta dot, but minus times, so we'll get cosine theta dot I, okay, but I'm not writing down theta dot here because it will come outside. Fine, so plus cosine of theta, its differentiation is minus times sine, so it will get converted to minus sine into theta dot j, but theta dot is, I'm keeping it outside from this also, keep it outside the brackets, so we'll get theta dot outside and also a theta here. Fine, theta dot into theta dot will be theta dot square, okay, plus from the chain rule of the differentiation, first we have to differentiate this, keeping this constant, and then this differentiating this, keeping this very thing as it is. Fine, so differentiating this into this, now we are keeping this very thing as it is, differentiating this very thing, so we'll get minus sine theta I plus cosine of theta j into differentiation of theta dot. Theta dot is differentiated again with respect to time, so we will get theta double dot. Fine, because it is differentiated again with respect to time. So from here, keeping this minus and minus outside, we will get here cosine of theta plus sine of theta. Fine, and cosine of theta plus sine of theta is already known to you as, I'll write it down first. Or double dot will be equal to minus times a cosine of theta I plus sine theta j theta dot square. So this very thing, a times this very thing, it is from here, it is r, it is the position vector itself. Okay, so plus here minus times sine theta of I cosine of this and theta dot square. This very thing, where it is, this very thing I have told you, minus times sine plus cosine of theta, it is represented, it is it gives the direction of the increase in theta denoted by this very thing. So this is theta hat and this is r vector. So we will substitute here theta hat or into theta double dot. Okay, and I'm missing something here. Sorry, I had double differentiated with this, but I have missed here. It is a here also, because a is constant in both the cases. Fine, so it is a here. Hope you are getting my point. Here a double differentiation, we are getting this very thing, and from this we know this is the position vector itself. So double dot of r will be equal to minus times this will be r vector into theta dot square plus a times this, a times, I will write it down this very first, and theta dot. This will give the position vector along the circular path acceleration of that. Okay, double differentiation of this position vector will give the acceleration along the circular path. Fine. So now there is a special case arising from this very thing. Let us see what that is. Fine. So we have got the result. I will write it down again. R double dot. This is the acceleration. Or double dot will be equal to, now it is given as minus theta dot square or vector plus a theta dot double dot and theta hat, unit vector along the theta axis, we can say. So considering that the circular motion is uniform. Fine, this is, say, equation A prime. So consider the case that circular motion is uniform. So what will we get? We'll be getting, that means circular motion, we have change in the theta with respect to time gives the velocity, that is the angular velocity. Okay, angular velocity. Fine, and double differentiation of this very thing gives the acceleration. Fine, so double differentiation, that is the theta dot, and now double differentiation will give the acceleration. But this is written as d by dt of theta dot. Fine, so we are considering that the circular motion is uniform, that is velocity of the particle is constant. that is the angular velocity here, because it's moving in the along the circular path. So we have to consider that velocity is constant. That means theta dot is constant. Fine. So that means theta dot is constant, and we know the differentiation of a constant term is always 0. That means this very term will lead to d by dt of dt, d by d theta dot of dt, that the double dot will be 0. Because theta dot is constant, that is angular velocity is constant, because the particle is moving with along the circular path with uniform velocity. So from the equation first, what we'll get from this equation, double dot r this term will vanish because theta double dot is 0. So from this very equation, r double dot will be equal to minus times theta dot square r vector. This will be the acceleration, even though the magnitude of the velocity is constant, but still then there is an acceleration. This is the circular path, particle is moving with velocity, constant velocity, okay, but still then it is facing an acceleration, and that acceleration is brought in by this very component, okay, because the direction is still unchanging, still going unchanged, even though the magnitude is kept constant, and this very term gives the acceleration along the circular path, even though the velocity is uniform circular path. The magnitude is constant, but there is a subtle acceleration felt inside this body, and this very acceleration is caused by the force, and force, we know force is the mass times the acceleration, okay. So in this case, F will be equal to minus times mass of the body times theta dot square, or because acceleration here it is minus times this very thing. So force will be equal to this, and it is also written as F is also written as minus times m theta dot. What is theta dot? This is the change in the angle with respect to time, that is the angular velocity. Fine, angular velocity. And here angular velocity we also represent it as omega. That's m omega square r vector. This gives the force. This is the force which produces the acceleration inside the body, even if it is moving with constant velocity. This force is called as the centripetal force, okay? Centripetal force. And the acceleration which it produces is called as centripetal acceleration. We can call it as centripetal acceleration because this acceleration is caused by the centripetal force, and this force is equal to and given by this very thing, because the component here, this very is vanished, but still then one component is still existing, and this gives the acceleration, and this gives the acceleration produced inside this body, even though it is moving with constant velocity. So this was all about the acceleration and velocity of a particle moving along the circular path in the orthogonal coordinate system, and how the centripetal force is producing this very acceleration inside the body. Okay, that's all for today. Thank you.